Okay, so it's a pleasure to welcome Igor Musevic from Institute Jožef Stefan in Ljubljana, Slovenia. Igor received his PhD from the same university in 1993, where he started as head of the soft matter research laboratory. He is a superb experimentalist, and he has won lots of awards over time. Just a couple are the 1994 Glenn Brown Prize for the best PhD thesis in liquid crystals, the 2012 Luckhurst-Samolsky Prize in liquid crystals. In 2018, he received an award from the Japanese Liquid Crystal Society, and in 2020, he was awarded the European Research European Research Project on Soft Matter Photonics Award. He's done lots of things, and we are right now in our group looking at Skyrmions and constantly looking at the work that Igor's lab has produced as sort of a guide into what we might want to do next. Normally in the field, Igor is there before anybody else. So please take it away. Go ahead, share screen.
Thank you, Chuck, for your kind invitation and nice introduction. So I will now first need to run the.
We need to give permission.
Host disabled participant screen sharing.
Okay.
Chuck, you are the host.
Multiple participants can try it again.
Yeah. So can you see now my screen?
Yes.
Mm-hmm. Okay, good. So the title of my talk is Skyrmions in blue phase 3 of chiral liquid crystals, and I have in fact double affiliation. So in addition to Jožef Stefan Institute, I also teach physics at the university. Now, this work is a collaborative work, and there's a lot of people involved, like 11 people involved, that started like 5 years ago. And that's a mix of optics, numerical simulations, light scattering, and chemistry in this project. And the content of my talk is shown here. So I will make rather an extensive introduction to liquid crystals. I will talk about different phases of liquid crystals, blue phases, and I'll make a connection to Skyrmions, which are most well known, I believe, in magnetic systems. Then we'll go to this work on blue phases, blue phase 3 liquid crystal materials. I will present how one can use an optical microscope to make really high resolution images of structures and take video microscopy to distinguish different phases in very thin cells. So we'll be looking at the phase transitions of these materials and the dynamics in very thin layers of this material. So we'll be exploring the DT phase diagram. So D stands for thickness of the material and T is for temperature. So the thickness of the material will be as low as 50 nanometers and going up to a micron or so. Then I will present numerical simulations of the phase. This is a very complex task. They are making really full tensorial simulations of the structure of these materials, including structures in bulk and in very thin layers where we shall see the single skyrmions in liquid crystal material. Then I will make a short note about skyrmions in liquid crystals and magnetic skyrmions to compare both, and then we'll go to conclusion. So let me first introduce skyrmions. I believe many of you are familiar with this, but anyway, to make a connection, it's good to start from the beginning. In magnetism, we have many manifestations of skyrmions, and there are two types of skyrmions which are presented here. So it's a block and a Needle type skyrmion in soft ferromagnets. So these arrows are spins, and in soft ferromagnets, the spins can be rotated in space, and due to chiral interaction, they really like to twist and splay. And the block skyrmions, which are shown here on the left-hand side picture, can you see my my cursor? Yeah. So if this is the center of the skyrmion, then on the periphery we have spins standing up, and as we go to the center, the direction is twisting along the trajectory, and the profile is shown here from up to down. And then up on the other side, we have a block kind of a vortex, right, of magnetization. And the second type is a Needle type, where the distortion is different. So instead of twisting, the magnetization is like a splaying from up to down state in the center. Now, the skyrmions were actually introduced as a model for mesons and baryons. There's a unified theory, field theory. And as I said, these are vortex-like excitation without singularity usual, which are observed in magnetism. So this is a TEM image, which can distinguish also the orientation of the spins of skyrmion lattice in a soft ferromagnet. And so this was actually one of the very first observation of skyrmion in very thin layers also, I must say. So this is basically a 2D systems. In liquid crystals, the theory of skyrmions was first developed by Bogdanov and Leonov in 2003 and later 2014. And they predicted vortices of not the spin, but the orientation, molecular orientation. I will go into details later on in my lectures. So very similar structures can be expected also in liquid crystals. And the first skyrmions to be observed in experiments in liquid crystals were these experiments. So this is confocal microscope imaging of skyrmions in the group of Ivan Smalyuk, where they were able to see the 3D structure of such a skyrmion in a liquid crystal. So it's a kind of like a bubble, and it's quite large compared to what we have in magnetism. So in magnetism, we have like 100 nanometers, and there's like several micrometers scale for skyrmions in liquid crystals. So let me take a note on the full, half, and quarter skyrmions in 2 dimensions, and then how this can be simply extended into skyrmion filaments in 3D, because we'll be dealing with this kind of filaments in this lecture. So if we take a block skyrmion here, and then at the periphery we have the spin down, and then the center we have spin up. And then if you plot all the directions that the spin takes, you will see that on a sphere, you have all directions occupied. It's the space is completely wrapped with the direction of the spins. So that's why the skyrmion is full skyrmion. So the rotation of the spin from the periphery to the center is pi. Now in half the skyrmion, the rotation is let. The twisting is less, right? So if here at the periphery the spin is parallel to the tangential to the circumference, it makes only a 90-degree twist, and this is it covers half space. The orientation of spins cover half space, and you can continue to fractional skyrmions like a quarter skyrmion, which are actually realized in blue phases, are occupying like one quarter of the space direction. So you can extend this 2D structure into 3D simply by repeating them, extending them, and then you get a full skyrmion filament. You can have a half skyrmion filament or quarter skyrmion filament. And there's a nice discussion of the relation between skyrmions in magnets and liquid crystals in this a nice paper by Duzgun, Selinger, and Saxena on 2018. Now, let me say a few words about the order in nematic liquid crystals. So liquid crystals, they're made of rod-like molecules. They can be like simple rods, they can be chiral rods, like twisting rods. So at high temperature, they are disordered, so no positional, no orientational order, but below a certain transition temperature, T and I, the system spontaneously orders. So all molecules, because of their interaction, align into a direction that is called a director. And this is a snapshot of this molecular orientation. And the degree of order is proportional to cosine square of this the tilt angle of the molecule with respect to the average direction of the orientation. So we have orientational order, but still the system is positioned in these orders. It's not a crystalline, and the system is anisotropic and usually is uniaxial. Now there are two important consequences of this spontaneous ordering. The first one is elasticity of such a liquid. So if here we see a liquid crystal, a nematic liquid crystal, and these lines represent the director, this director can be bent, it can be distorted. So we have a liquid that can be elastically distorted, and it can transmit torques in this liquid. The orientation order also gives rise to birefringence, because these molecules, they are all ordered, the system is uniaxial, and there's a large birefringence, one of the largest that can be observed in condensed matter. So this is an example of a nematic liquid crystal between crossed polarizers. You can see the smooth structures which are indicating this is a liquid. Beside the smooth structures, we have topological defects. So please have a look here. You can see a cross between dark brushes, for brushes between cross polarizers, and there are always pairs of topological defects, which is connected to actually to a conservation law, the conservation of the topological charge or winding of these defects. So if you look at this as one of these defects, these brushes are directed along the polarizer P and an analyzer A, and in the center there is a singularity in the orientation. That means in the center of the defect, the system is disordered. It does not know in which direction to order. If we take chiral molecules, they're briefly mentioning, they are different from their mirror image. The hand is an example of such an object. Molecules are examples of such objects. And these chiral molecules, they like to twist. So they make this biological twisted structures. And if you take chiral liquid crystal molecules, that means molecules which like to make a liquid crystal phase, that means ordered phase, and they are chiral, we have very interesting effects of this chirality. The first and the simplest chiral phase is the so-called holosteric phase. And this is obtained for low chirality of the molecules. And we have spontaneous twist in one direction, in X direction. So in Y direction, the system is still homogeneous, but in X, it's periodic. So we have a spontaneous formation of a helical structure along the X direction. Now, if we increase the chirality of molecules simply by changing the chemistry, liquid crystal does not twist only in one direction, but it likes to twist in two orthogonal directions, or even three, right? So we have a situation where we have two directions, orthogonal directions of the twist, and this is shown here on this right picture. And in this case, we can see that it can easily form a double twist cylinder or a Skyrmion filament, such a material which tends to twist in two orthogonal directions, right? So if you look at this cross-section encircled, you see that this cross-section is actually a Skyrmion cross-section, and we have a Skyrmion filament. So this double twist cylinder, as it's called, is actually radially twisted cylinder or a Bloch filament, if you want, comparison to the magnetism. Now, blue phases, I will show some photographs of these phases, are natural candidates for many different or 3 different Skyrmion-like structures in bulk. So molecules are chiral, highly chiral, and they like to twist in 2 or more directions. And we obtain phases which are quite different from the rest of the liquid crystal phases. So some examples are shown here. So you can see blue, it's actually crystallines, right? You don't have any more the smooth structure, but it's a crystalline structure with several different crystal orientations, different colors. And those different colors, they're usually blue. That's why blue phases, but they can be also red, green, yellow, whatever. It depends on the orientation of the local orientation of the crystal with respect to the illuminating light. So there are more examples here. And if you zoom in, you can actually see that those blue phases, which are still liquid crystals, they are periodic. So they are a mixture of crystal properties and liquid properties. So these lines that you can see indicate arrangements of molecules and periodicity in blue phases. Now, it was in 1969 that Alfred Saupe proposed that these double twist cylinders be the building units of blue phases. And he proposed the simple idea that you have a cubic crystal where the crystal is formed by these double twist cylinders, which is shown here. And of course, if you look now from the periphery to the center, we have a half Skyrmion, and then this continues, and we have a topological defect here in between. And of course, this idea was then developed, and this is a picture of a single filament. And if we want to pack these filaments into a 3D structure, we see that there are some problems in packing problems. So if you pack 2 cylinders, one with the axis vertical and the other with the axis horizontal, you can see that along this axis it smoothly connects if we have a quarter Skyrmion, right? But if you look at the space between different cylinders, so 3 cylinders, you can see here that there is a place where we must have a defect, because the molecules here from these cylinders, they align in this direction. On the neighbor is like this, and then on this neighbor is like this. So we have a kind of frustration. And this frustration actually is a topological defect, which is located here in the openings between the cylinders. And this is not actually a single point defect, but it's a line. So it is extending throughout the crystal. And this is the picture of the schematic picture of the blue phase 1 and blue phase 2. So in blue phase 1, the defect lines do not connect. We have the simple stacking of double twist cylinders. And in BP2, we have another cubic structure. And in this case, the defect lines are connected. They are forming vortices. And this is in more detail described in this review paper by Wright and Mermin from 1989. So because of this 3D periodicity, blue phase 1 and blue phase 2 are photonic bandgap materials. That means they are reflecting light because of the periodicity of the dielectric tensor. And they are actually crystals which are made of topological defects, right? And they reflect, interestingly, circularly polarized light, which has the same handedness as the double twist cylinders. Now, these phases are stable phases, and they exhibit an interesting and quite general phase diagram. So on the y-axis, we have the temperature, and on the x-axis, we have the mole fraction of chiral. Ce5 is a material that is highly chiral and forms the blue phases. And we can make a racemic mixture, which means equal number of left and right-handed molecules. And then if you look at the you are adding chiral molecules to the racemic mixture, you start from 0 and you increase chirality to pure material. And then you can see what are the phases. So this is determined by heat capacity measurements. You can see that here above you have isotropic phase, and then you have one-dimensional, this helical or cholesteric phase. And then there's a region of blue phases. Here is quite general. You have BP1 at lower temperature, at higher temperature, close to isotropic, you have this BP2, and there's a very interesting and for a long time unknown BP3 here, which is at high chiralities, high temperatures, and the phase ends here at the critical point, which is actually a supercritical point, which means that you can come from the isotropic phase smoothly into the blue phase 3 without any heat capacity change, actually. So the structure of blue phases are shown here. So we have 2 cubic phases. By increasing temperature, we come then into the BP3, and BP3 was considered to be a molten phase of this double twist cylinder. So we have crystal BP1, we have crystal BP2, and we have a fluid. We have a fluid, BP3 is a fluid of skyrmions. So there are many indications of that BP3 is actually a skyrmion fluid. That means a fluid of skyrmionid filaments, starting from Marcus in 1981, when he described this as a blue fog. You will see that this is actually a kind of foggy phase, nothing special, right? And he proposed that this is a liquid version of the crystalline blue phases. And the first a kind of argument for this disordered skyrmion filaments was in the 1986 when they were doing freeze fracture electron microscope observations of blue phase 3 materials that were rapidly quenched. So you can see here that after breaking the crystal, you can see some structure which look like filaments, right? And they are completely disordered. So are these filaments actually twist cylinders, right? So what are the facts about BP3? The structure at the moment was not known when we started this experiment. It appears bluish, but has no periodicity. The reflection spectrum is broad. There's no sharp black reflection indicating any periodic arrangements of these double twist cylinders. And its bluish color must originate from light scattering. So the same phenomena that we observe with blue sky. So the conjectures were that if this is a disordered fluid of some grains which are scattering the light, right, to make it bluish, then if there are grains, they must be grains of ordered chiral nematic. And if there's ordered chiral nematic, there must be topological defects, right? So the aim was to experimentally observe details of the structure. That means going down to the very small scale and try to see defects which would be a clear indication of the skyrmionic nature of blue phase 3. So these pictures was at the time supported by numerical simulations. So this is from the Edinburgh group, and so Heinrich, Stratford, Cates, and Marenduzzo. They made the simulations of the excuse me, of the highly chiral materials, and this is what they get for the phase that they considered to be a blue phase 3. So what you see in blue are the defect lines. We call them disclination, and the blue line. The blue lines, they show the contours of the order parameter. So the degree of ordering of a liquid crystal. So inside it is disordered, outside it's more ordered. So you have twist cylinders which are somehow entangled through this mesh of defect lines, which are, as you can see, interconnected. They join into vertices and so on. So it's a kind of indication of a double, actually, network of double twist cylinders and interconnected with a network of defect lines. And they calculated the structure factor, and which should be visible in light scattering. It's a liquid-like, so it gives rise to isotropic scattering. So how to confirm the existence of the Skyrmion filaments in blue phase 3? So actually, we followed a kind of idea that was developed in a similar study on a spontaneous formation and dynamics of half Skyrmion in blue phase 1 material. So this is a kind of a mixture. And when this mixture is confined to a very thin layer, it was predicted by numerical simulations that the hexagonal lattice of Skyrmion be stable. So we have vortices showing the twist of the molecules from the periphery to the center, 90-degree twist. And we have here topological defect lines, which are running perpendicular to the to your screen. So it's a very thin layer, 50 nanometers, 100 nanometers, and it was predicted that blue phase 1, which is cubic, should transform into this hexagonal simple lattice of Skyrmions in very thin layers. So these are half Skyrmions and the defect lines, and I will also speak about defect lines later, but just to show the director orientation around such a line here at the in between the Skyrmions. And this is the side view. So half Skyrmions cannot be packed into the lattice without having singular defects. So we'll go to the video microscopy, which was used to observe this, the structures. So we use a simple optical microscope. Actually, it's not as simple as it, so it's the best microscope that you can have. And then you use a narrow band, but still not coherent illumination. You choose a blue wavelength to have the lowest, the highest resolution available. Diffraction limit is the narrowest. And we observe structures in reflections, and we use a very large numerical aperture objective and perfect English matching. So with this, we obtain the resolution of an ordinary optical microscope of 150 nanometers. And this is an example which shows a comparison of such a microscope with comparison with confocal and STED microscope on different materials with decreasing periodicity or pitch. So here you can see a kind of periodic liquid crystal, which has a period of something like 200 nanometers. And then we shorten the pitch of this material to 150 nanometers, and we can still see the periodicity, but it's lost because we have reached the resolution limit and we don't see anything for shorter pitches. Now, you can see that confocal is not even so good as a good microscope. The advantage, of course, is that you can look in 3D. And the STED microscope is superior as you can go down to 90 nanometers in liquid crystals. And this was just studied like 2 years ago. So when you use such a microscope in very thin layers of blue phase 1 material, so this is 140 nanometers thin planar layer. So we use 2 glass slides, and in between we put a layer of this liquid crystal. We assure that molecules are properly aligned at the surfaces. And what you can see a hexagonal network. These dark spots are Skyrmions. And unfortunately, we can't see the defects because they are too small. And you can see interesting white spots, which are fluctuations of the interconnections in between the Skyrmions. So this is something which is really one-to-one correspondence to the numerical supulation. So we have a 2D hexagonal crystals of dark spots, which are Skyrmions. Now, in even thinner samples, we can see individual Skyrmions. So these large black dots are Skyrmions, and you can see 2 defects here. So it's interesting to yeah, to see that the defects are actually quite free from and they just wander around, sharing between the different skyrmions is observed. So it's like two liquids which are mixed together, a liquid of defects of -1/2 winding. I will say immediately what this means, and the skyrmions, which are not singular objects. So you can see that each skyrmion is accompanied by two dark spots, which are seen here with two defects. And such a defect is characterized by the winding number. And it's very simple to realize what the winding means. So here I have two examples of +1/2 defect and -1/2 defect. You can see there are two different configurations, and you characterize the winding number by going along a circular path in clockwise direction, and then you look at the rotation of the director. So we go from this side to this side. You can see the director has rotated, right? And it has rotated clockwise, and it rotates for pi as you return when you make a closed loop. And this, so that means that you make a pi rotation of the director, and this is then defined as the +1/2 winding, because it's positive direction of rotation. And this is the counterpart. It's the -1/2 defect. You can see how this director is rotating in the opposite way compared to this one if you go along the closed path in a clockwise direction. So there are two defects. And so we have a picture of skyrmions. So here is the center. And of course, the winding or the charge is +1. And it must be accompanied by two -1/2 charges. You can see here is the characteristic defect with threefold symmetry. And this compensates for the total winding or the total topological charge of the system. So we use the same approach in blue phase 3 material. So these are the details of the structures. You can see that it's blue. It's blue and there are no details. It's just bluish, foggy. It looks foggy under the microscope. If you make a wedge cell, the wedge cell is a cell where the thickness here is different from here. Then for a periodic phase, BP1, you can see the different layers, right? So it's layering which accommodates different thickness, but in BP3, you don't see any layering, right? So it's indication of no periodic structure. So if you look at such a sample in a temperature gradient, so here we have a low temperature, and here up is high temperature. It's a several Kelvin gradient. Then you can see isotropic phase here, and then you can see there's a phase transition. Actually, it's very difficult to see it from these pictures, but using other methods, we can locate the phase transition between the isotropic and blue phase 3 here. And then there's a second phase transition from blue phase 3 to blue phase 1 here, right? So we have a continuous phase transition and discontinuous second order and first order phase transition. So if you measure the reflectivity of the sample, then so this is the zero of the temperature is set at the isotropic blue phase 3 transition. You can see no it's white reflection, right? But when you go to blue phase 3, you can see reflection starts here, and this is around the blue range. So this indicates the appearance of the blue fog. And there's no sharp peak. And this sharp peak appears in blue phase 1 when the crystal is formed. The 3D crystal that reflects, Bragg reflects a characteristic wavelength. And that's what the origin of the colors, which I have shown on the images. So let us look at the phase transitions and dynamics of this material when you confine it into very thin layers, starting from 1 micron down to 50 nanometers. So this was actually one of the first videos that we took when we started the studies, and I was shocked when I saw this picture. people thought this is nothing special because it's all disordered and so on. I don't think so, because what you see are dark spots. So look at the scale here. So it's 500, this is half a micron. And then you can see fluctuating dark spots appearing and disappearing on the time scale of several seconds. And this is illuminated with right-hand circularly polarized light. And if you take the left-handed circularly polarized light here, you can see nothing actually. So it's indication that we have something which is very dynamic. It's very slow. It has dark spots which look like skyrmions in hexagonal lattice, and they reflect circularly polarized light. So there are very many arguments for saying that these are actually filaments which emerge from the glass. So you can imagine a glass surface. You're focusing your microscope on the glass interface, and then you can see when this skyrmion filaments are popping to the glass, and they detach. So it's very dynamic. So this was the picture that we built when looking at this video. So if you take a snapshot and you make a Fourier transform, you get something which is very similar to what was calculated from numerical calculation of Cates and Maranduzzo. So you have a ring with a 250 nanometer diameter. So this would be like an average distance between the dark spots. So the question is, are these dark spots skyrmions, or the ends of the skyrmion filaments? And what is actually the dynamics of blue phase 3? So let's start from the bulk. In the bulk, we have two methods to detect the blue phase 3. One is the optical activity. And you can see that the optical activity increases from the 0, which is in the isotropic, nearly 0 in the isotropic phase. So it's a very clear indication of the phase transition from isotropic to blue phase 3, and then also to blue phase 1. So we use this measurement in order to determine the phase transition temperature, because we are using different setups with different gradients and so on. So we are using this optical activity as a scale, as a ruler, which says at what temperature is the isotropic blue phase 3 transition, at what temperature is by BP3 to BP1 phase transition. And then the second picture here is the relaxation frequency. So this was done by dynamic light scattering. In dynamic light scattering, you are measuring the fluctuations of the, in this case, the birefringence of the local axis of this material, which is obviously strongly fluctuating and is strongly scattering light. You can see it with the bare eye, right? And this is very interesting because previous studies did not focus actually on the number of relaxation branches which are observed here in BP3, and we can clearly see there are two branches which are shown in more detail here. So we have the first branch, which is here, which is slowing down in the isotropic phase. So note this is a logarithmic scale, and this is something which we know as a soft mode. So it's a condensation of the order in liquid crystal, which leads finally to an nematic phase. But before we reach blue phase 1 here, we have blue phase 3, where the single mode clearly separates in two modes. I mean, there's such a big difference in order that you can't miss it. So we have a low frequency and a high frequency, and there's an order of magnitude of difference in this relaxation rates. So what does this indicate? So in a simple picture that we built, it's like this. So suppose we have filaments in blue phase 3, and these filaments are fluctuating. Then the fast mode would represent the internal twist and distortion of this filament, and the slow mode would mean the slow hydrodynamic movement of this huge disclination lines, which are tangled to each other and so on. And that's why one can expect that the relaxation modes of this fluctuation of the filaments as a whole is so slow. Now, to reveal the true structure of these filaments, we made very thin with cells down to 50 nanometers, where we observe the following. So this is actually one of the central parts. I will use the pointer now of the study. So this is the phase diagram, the temperature and the thickness. So we start at 50 nanometers and go up to 1 micron, half a micron, and each point is a measurement. We take pictures and videos of the structure. And you can see that then we have 1, 2, 3, 4, and this is the 5th phases. So the white one is the isotropic at higher temperatures. Now this light blue is BP3. We know this from the bulk, right? And then we have this yellowish, right, or orange is blue phase 1, so BP3, BP1, and then there's the first order phase transition here, right? We can see it from dynamics, from the optical rotation and so on. And this transition line, as you go to lower thicknesses, ends here. And suddenly, both phases, BP3 and BP1, transform in another phase, which is shown here. So this is point B, it's panel B, right? So we have skyrmions at below 150 nanometers. I will show also videos of the skyrmions. And then if you go to lower thicknesses, so this is panel A, you can see individual skyrmions. So these, the green, are individual skyrmions, like a gas of skyrmions. This is the liquid of skyrmions. And what is most important, BP3 and BP1 both are made or are born out of the skyrmion fluid, and the critical thickness for this transition is around 150 nanometers. So below we have a skyrmion liquid, and above this thickness we have either BP3 at higher temperature or BP1. So let's look at the videos of just at the critical thickness just below, where we have dense skyrmions. You can see it's strongly fluctuating. If you go to lower temperatures, at higher temperatures, then you can see this motion is much more vivid, right? So these dark spots, they move faster, they disappear faster, everything is faster. And then if you go to lower thickness, you can see individual skyrmions. It's a skyrmion gas, fluctuating still, moving around, lingering. Sometimes we see annihilation of skyrmions. So one of the interesting properties is the skyrmions, they can simply disappear, right? So the number is not conserved. And if you hit them up, then you will see, so here's the temperature approaching the isotropic phase. You can see that the density is increasing. So the skyrmion gas is somehow getting denser and denser, and then it transits into the isotropic phase. So on the other hand, if you go through BP1, BP3 transition, so this is the low temperature, BP1 is clearly crystalline, right? And if you look at this region, you will see how it melts. And one can clearly see there's always like a interface in between, which means that this is the first order phase transition. So very interesting is the dynamics of skyrmions in thin cells. So in thin cells, you can't actually use the normal dynamic like scattering, but we used another technique, which is cross correlation video analysis, to simply take pictures and then you differentiate, you look for difference in subsequent frames. And from here, you can reconstruct the dynamics, very similar to what you do with the DLS. And these are the paths. So we made temperature scans here at very thin layers, thicker layers, but still below the critical thickness, and here at very high thicknesses. And you can see the dynamics. So this is the rate. We have two modes, even at this lower, very low thicknesses, so the same as in bulk. We have a fast rate and the slow rate. So the slow rate in hertz is very slow indeed. So it's several hertz, right? So these are red points. So this represents this slow movement of individual skyrmions the time scale for this movement is something like 1 Hertz. And there's another mode, which is here in kilohertz. It's not so fast, it's hundreds of hertz. And this represents the internal dynamics probably of the skyrmions as they change. And then you can still see the soft mode or the slowing down of the fluctuation in the isotropic phase. And the same picture is for the liquid phase, isotropic to dense skyrmion phase, and from the isotropic through BP3 and then through BP1. So very slow relaxation rates of dense are characteristics of dense and isolated skyrmions. And this is also seen on the correlation functions. So these are autocorrelation functions and different thicknesses. And these tails, they are actually indication of the presence of skyrmions. Even you can't see with the bare eye under a microscope, you can detect them in this correlation function. So I will go briefly through the Landau-Degen modeling of BP3 in bulk and very thin layers. It's quite a sophisticated method. It's based on the tensor order parameter expansion, where you take into consideration local degree of ordering. It's order parameter S, as we call it, and local orientation. That means you look also at the elastic deformation, and then you minimize the free energy, and this is the result for a given chirality. We actually reproduce the results of Cates and Maradutov's paper. So in this yellow is the mesh of the -1/2 defect lines. You can see here, right? And in the center, if we look at the cross section, you can see this threefold symmetry defect. So it's a -1/2 defect lines which are merging, and they are entangled with another mesh, which is a mesh of double twist cylinders, which are shown in blue. So the cross section here is something like a quarter of a skyrmion. Now we can also look at the, so this was in bulk as I showed, and in very thin layers. And so this is the example for 300 nanometers. You can see there's defect lines emerging from the surface, and the skyrmions are formed in between. Now we've also made analysis of the image of this of the structure by considering birefringing and everything, and this is the simulation. The optical image simulated as if you were looking through a numerical microscope, so to say, and this is the experiment. So you can see very good correspondence of the optical appearance of such a structure in reflection under a microscope. And this is the lower one is at lower thicknesses, 130 microns. That means below the critical thickness, where you can see the isolated skyrmions in simulation, and you can see the same in the experiment. And this is the analysis of the twist. I will come back in a moment to that. So because we are able to calculate the twist of the cylinders, we are able also to calculate the distribution of the twist, of the radial twist for the structures. And this is done for 3 structures. So this is for the lowest one, 130. And this is this indicates the number of values which we detect. So this is the radial twist, and you can see the maximum is here, right? And this is close to 90 degrees. So in very thin layers, we actually have something which is similar to hexagonal lattice of skyrmions, of half skyrmions, and the radial twist is close to 90 degrees. Now, if you go above the critical thickness, remember this is 150 nanometers, then you can see that the peak of this distribution goes to lower, so it's around 50 degrees, and in bulk, we can see it's even lower, it's around 40 degrees. So this would mean that we have here half skyrmions, 90-degree twist, and in bulk, we have something which is close to quarter skyrmions, but lower, it's around 30 degrees twist. So let me briefly discuss the the magnetic skyrmions and the application point aspect of view, and the liquid crystal skyrmions. So you know that skyrmions are proposed to be used as bits of information. Why? Because they are localized, they are particle-like structures, they can be annihilated or created, they are topologically protected. Topological protection means that you cannot remove them otherwise but cutting the field or melting the field. So there's an energy barrier between the skyrmion state and the homogeneous state, which gives the so-called topological protection to the system. And in magnetic skyrmions, the interesting physics was observed for this magnetic particle-like structures. So it was proposed to move them by currents and so on, to detect them in different ways, and to use them as information storage devices. They are quite small, but not always so small. If you look at the room temperature, you can barely see a skyrmion that would be smaller than 100 nanometers, right? And they are difficult to stabilize at room temperature. They can be driven by electric current. They are polydispersed in size. They're difficult to produce. You need many layers of different materials to make them, and they're difficult to detect. Now, in this BP3, we have practically the same diameter, so it's around 90 nanometer room temperature. We have several Kelvin around room temperature where the interval of stability. They can be driven by light. This was shown. They can be driven by electric field. They are very uniform in size. They are simple to prepare. And we think that by taking even higher chirality materials, we could go down to less than 50 nanometer skyrmion. And what is most interesting, they can be detected optically, right? If you fluorescently label them, you can distinguish orientation of this fluorescent molecules in the skyrmion, and this could be a simple and very fast method of detection. So let me come to conclusions. So there's, I think, a lot of evidence, clear evidence that blue phase 3 is a topological fluid of tangled skyrmions and defect lines, -1/2 strength defect lines. We have a perfect agreement between experiments and theory. And these skyrmions made from BP3 materials are actually competitive to magnetic skyrmion. And interestingly, a similar phase was proposed for magnetic systems. In some magnetic system, the theory predicts the quantum blue fog. Actually, if you look at this, this paper, is exactly the same theory as for the blue phase 3. So it's a BP3 analog in quantum world. So this work could be a guidance for those experiments. And I think that most important message is that the relaxation rates and the number of relaxation branches should be 2, right? So one representing the internal dynamics of skyrmions, and the other representing collective movements of skyrmions once they are formed, either in BP3 or in spins. And this was published recently. So again, I would like to acknowledge the contribution of my co-workers, and I would like to thank you for your attention, and I will be happy to take questions.
Thank you very much, Igor. It's really interesting. It's a lot for us to catch up on. So let me first throw this open to anybody else who has some questions. If not, then I will go ask.
I have a question. Can you hear me?
Yeah, I hear you. Yeah.
So I was wondering, as someone who mainly thinks about magnetic vortices and skyrmions, so the you know, the like sort of be useful for memory storage. but then it turned out that moving them was too difficult due to pinning. And so then Skyrmions came along and I thought, well, the thing that was really attractive was that they were maybe possible to move very quickly with low fields, because they were thought maybe they wouldn't pin as much as.
Well, I'm losing the audio. Sorry.
Yeah, Jesse, you're cutting in and out, audio-wise.
Perhaps you switch off the video.
Maybe,
so.
Yes. Okay. So I was saying that. Sorry, my question was already rambling. That with magnetic vortices, they were hoped to be good for memory storage, but there was too much pinning, and they took too much electric field to move. Too dissipative. And then Skyrmions were hoped to be able to be moved more quickly with low field, and maybe that's true or not. And so I was wondering if it's, I mean, in terms of using them for storage, you're talking about comparing the two. In terms of speed or energy, is there how those things compare, and whether there's a difference between using vortices in a liquid crystal and using Skyrmions in a liquid crystal?
Well, as I said, thank you for this very interesting question, which is also challenging because many things about moving Skyrmions are not quite well known, right? We have there are clear proofs that Skyrmions can be moved by electric field in liquid crystals. Now the question is, to what degree can this movement be controlled, right? So it takes a lot of efforts probably to design and construct devices actually where you would make dedicated experiments with electric fields and move these things around, right? So there's a work of a group of Ivan Smiley from Colorado University exploring that, but I'm not sure whether the numbers are there already, and also the scale is quite different. So we usually we are observing large scale Skyrmions, whereas these Skyrmions are very small, right, and could be made even smaller. And when you come to such a small dimension, probably you must switch to some kind of fluorescent detection to track their motion, right? Because they're so small, they will not be visible under reflection because the reflection will be very, very small. Even in these images that I have shown, they're taken in reflection, and you can. I mean, it's like less than 1 promille of the intensity that you capture. So if you decrease the size, I think you need to take another method, and this is fluorescence. And fluorescence means labeling these materials with molecules, organic molecules that align with liquid crystal. And then, of course, they also move. When the structure moves, the alignment changes, so you can follow. I'm convinced, we haven't proven that, but I'm convinced you can follow optically even very small Skyrmions because you are not limited by diffraction, right? You can see the point source, right? So if there's hopefully enough light and fluorescence is quite strong, you can detect it easy. I think you can follow the motion of this part of the Skyrmions in liquid crystals actually very simply using an ordinary microscope. You simply excite the fluorescence and then you see. You don't see the very details, but you see the particle movements moving. And of course, this requires dedicated experiments which have not been designed yet. The most important, I think, observation is in this phase diagram, if you remember. So the temperature interval of the stability of this phase is 4 Kelvin and even more, right? So these experiments should not be difficult. You can work at room temperature, so you can use fluorescence and so on. But as I said, this has to be done. So we have I cannot answer in numbers, right? Except for the size. I'm sure that the sizes can be made very small, right? And at room temperature, yeah.
Anything else? Oh, Shule.
Hi, Igor. Thanks for the very informative talk. I have actually two questions. One is about the detection of skyrmions in liquid crystal. You mentioned the optical measurement detection. So for magnetic skyrmions, magnetic skyrmion can be detected either by either optically or through the transport measurement. There's a topological Hall conductivity, which is proportional to the density of skyrmion. Is there something like that? That's in terms of detection of crystal skyrmion in crystal, liquid crystal.
There's nothing like that because well, these are insulating materials, right? Highly insulating. So because you want them to be highly insulating for use in this space, right?
Yeah.
And if you introduce charges, which can be done, right, then you have a lot of dissipation. So the research in this direction was actually stopped in 1980s or so. So people have focused on very good dielectric materials with very low electric conductivity, and this provides use of electric field, right? Rather than current, you induce transformation of the structures by field, right? So typically you make a cell which is made of glass, and you have one transparent electrode here, the other here, and then you have a skyrmion in between, right? And when you apply an electric field, you use a very small amount of current, right, to use the torque of the electric field on the dielectric anisotropy of the material, right? So you are producing torques with the electric field, and that's why the power consumption is so small, right, in LCD devices. Now, the observation of this birefringent materials can be done by polarizing microscope and video imaging. However, as I have said, this has a limitation. It's Abbe's resolution limit, right? So you can go down to 150 nanometers or so. But we know that you can track even single molecules, right? Fluorescent molecules. So you simply, the idea is to dissolve molecules which emit light in the material. And these molecules, they are in many cases a kind of rods, and then they align with respect to liquid crystal. That means you have emitters of light which are aligned, right, with the liquid crystal. And if you have different orientation, the intensity is different with respect to excitation and emission. So you can distinguish actually the orientation of the molecules, right? And in such a skyrmion structures, you have seen for full skyrmion, you're covering the whole space, right? So it means your emission will be in whole space, right, where the skyrmion is. And if such a skyrmion moves, you can follow it simply by taking the fluorescent image, which can be very fast, right? So you can trap them not with electricity, but with analyzing the images, and so it's completely different, right?
I put up a paper, so it's a series of the skyrmions in liquid crystal, and I see in the energy density functional, I see a electric field related anisotropy term and also magnetic field related anisotropy term. So I assume that the one can also move the skyrmion in liquid crystal by magnetic field.
Yeah.
In that sense?
Yeah.
Okay.
So magnetic field effects are not so strong as for the electric field because you have highly polarizable molecules, right? You have a dielectric constants of, I don't know, 20 in one direction, 5 in the other direction, which means you have strong anisotropy, and that couples very strongly to field, right?
Yeah. So
you need only a couple of volts for a 5-micron display to operate, right? And it's the same here with skyrmion. So in a skyrmion structure, the field couples. In the free energy, you have a term which minimizes when the molecules are along the field, right? And that causes the transitions from one state to another state, even in the small scale, right? For small scale, you would need large fields, right? because you have the short modulation, which means higher energy, stored elastic energy, and to make transition to another structure, you would need, I think, quite strong fields, which could be a disadvantage in let's say writing or deleting skyrmions, right?
Okay, thank you. I actually have another technical question, but I want to see if anybody else want to ask a question first.
Is it?
Yeah, Yuhao, son, go ahead.
Okay, thank you. So I have a basic question. First, thanks for the nice talk. So my question is, are the liquid crystal skyrmions on a special type of topological defects in liquid crystals, or it's another interpretation of the conventional topological defects in liquid crystals? Just like are they special compared to other topological defects?
Well, you have different classes, right, of topological defects, and the skyrmions here are non-singular, right? So these are smooth soliton-like structures, which sometimes we look at them if we look at them as isolated structures, you can't actually create them isolated from the background, right? So you need to embed the structure, solitonic structure, into the background, which can be different. It can be homogeneous or non-homogeneous, and then you need to have other structures which are topological defects to actually form this kind of structure. For one example was this half skyrmion that I have shown, you remember, right? So it's a skyrmion, this big dark spot, which is non-singular, it's smooth, there's no discontinuity of the field, and then there are defects. So the reason for this is simply the conservation of the topological charge, right, of this kind of systems. So that's, I would say, they can't be isolated, right? They are always embedded into something, and that brings singularities in many cases, not in all cases, but in many cases. So I have shown here filaments, but in liquid crystals you have other types of structures, which are, for example, the Toron structures is quite complicated. 3D structures is really localized, it's not a filament and so on. And there also you have a combination of solitonic structures and topological defects. So somehow this goes together in nature, right? In 3D, yeah.
So skyrmions are kind of a combination of the smooth solitonic,
yeah,
combined with the topological defects with singularities.
In reality, yeah. In reality, we always see this combination, right? Not always in 3D. I'm not aware of any structure. Chuck, perhaps you can correct me, but is there any 3D smooth solitonic structure in liquid crystals without defects, topological singularities?
That comes to mind off the top of my head.
Yeah, yeah.
Okay, thank you.
Okay, we are running somewhat after, and so what I'd like to do is sort of release people to go about doing their business, and stick around here if you want to, if there are some other questions that you may have. Shule, did you want to ask another question?
Yeah, let me first stop recording, then we have the informal.
Oh, good. Yeah, good point.